Hello and welcome to the second video on my Calculus 3 or Multivariable Calculus problem solving series. In this video, we're going to look at two approaches to find the equation of a plane that passes through three non-collinear points in 3D. Okay, so this question asks us to find the equation for a plane that passes through 3 points. So there are two approaches to this problem. The first approach is a parametric equation which uses vectors. So the equation has two parameters, alpha and beta, and the output of this equation is any point on the plane. So as alpha and beta change, we're moving on the plane. The equation consists of a starting point, r0. Well, when I say the point r0, I really mean the vector r0, which points to a known point on the plane. Later, you'll see that we'll use the point P as r0. So we use r0 and two non-collinear unitary vectors, which I'll call u and v. So to get any point on the plane, we're adding our starting point plus a multiple of these vectors, a combination of these. So for example, in this case, to get from r0 to r, I'll walk 3 steps in the direction of v and 1.2 steps in the direction of u to get to r. So to get the entire plane, alpha and beta will range from negative infinity to infinity. This approach is also similar to what we saw in the first video for the equation for a line, except that in this case, it's a 2D plane. So the second approach that we're going to be looking at is a Cartesian equation which uses a normal vector and a parallel vector to the plane. The normal vector is a vector that makes a 90-degree angle with the plane. So it is sticking straight out of the plane. And the parallel vector that we're going to be using is going to be r minus r0, where r0 is a known point on the plane and r is a point, any point on the plane. So this will give us a parallel vector to the plane. So we can say that r0 is equal to x0, y0, and z0. This will just be our starting point. And r will be equal to x, y, z. This is any point on the plane. Then that means that n will be equal to nx, ny, nz. So the method that we're going to be using to find the equation for this plane will be the dot product, because the dot product of two perpendicular vectors will always equal 0. So we can say that nx, ny, nz dot x minus x0, y minus y0, z minus z0 is equal to 0. And then we perform the dot product by just multiplying each of the components and adding them all together. And when we simplify, we get that nx times x plus ny times y plus nz times z is equal to nx times x0 plus ny times y0 plus nz times z0. And this equation you might recognize from the equation to a plane. So where a is the x component of the normal vector, b is the y component of the normal vector, and z is and c is the z component of the normal vector. And d will be this here, this constant here. So using this, we can get the equation for the plane. Alright, let's look at the first approach on how to find an equation to a plane that passes through three non-collinear points. Remember that for the first approach, we need to find unit vectors, two unit vectors that are parallel to the plane. So to do this, we're going to use the vectors PQ and PR. So we find that PR, we're going to have PR is equal to OR minus OP. And PQ is equal to OQ minus OP. And then we can solve, and it's going to give us these vectors here. So these are the vectors that are parallel to the plane. The next step is to find the magnitude of these vectors. So the magnitude of these vectors is going to be the square root of the sum of the squares of the components. So for PR, it's going to be the square root of 126. And for PQ, the magnitude is going to be the square root of 72. To find the unit vectors, we need to find PR divided by the magnitude of PR. And to find the unit vector for V, we need to do PQ over the magnitude of PQ. So that's going to give us these two vectors here. These two vectors are the unit vectors that are parallel to the plane. The next step is to plug these into the equation. So the equation here we saw earlier. So we need a starting point and the two vectors. We have the two vectors. And for the starting point, I'm going to pick the point P. So R0 is going to be OP, which is 10I plus 2J. So now we have everything we need to plug it into the equation. So when we plug it into the equation, we have our starting point plus alpha times U plus beta times V. And remember that alpha and beta range from negative infinity to positive infinity. That is what give us the infinite plane. So then we can simplify and distribute, and then we can simplify and combine the like terms. So I'm combining all of the I components, all of the J components, and all of the K components. And this will give us this equation for the plane. Now, since this is a parametric equation, you can also express this as three different equations for each of the components, just as we did in the last video for the line. Except that in this case, each of the components will have two parameters instead of one. And remember that alpha and beta range from negative infinity to positive infinity. So as alpha and beta change, you're moving along the plane. So yeah, that's how you can get the equation for the plane using the first approach. Now let's go ahead and look at the second one. Alright, so to find the equation of a plane using the second approach, we need to find the normal vector to the plane. The normal vector is a vector that makes a 90-degree angle with the plane. We also need to find this vector, which is a parallel vector to the plane. And this vector goes from the point which the vector R0 points towards to R, which points to any generic point on the plane. So once we have the normal vector and a known point on the plane, we can put it into this formula, which we saw earlier, to get the equation for the plane. So to find n, the normal vector, we're going to use these two vectors here, PQ and PR, which are two parallel vectors to the plane. So to find n, we need to find PQ and PR. So just as we did in the last approach, PR is going to be OR minus OP, and PQ is going to equal OQ minus OP. And then you get these two vectors. So with these two vectors, we're going to find n, and R0 is going to be OP, which is going to be our starting point. So 10, 2, 0 is going to be our starting point. And we're going to use these two vectors to find n. So the way we find n with those two vectors is we're going to perform the cross product. The cross product of two vectors is another vector that's perpendicular to both vectors. So the cross product of PQ and PR is going to be a vector that's perpendicular to both of them. So to find the cross product, we need to set up this here. To set this up, we need to write the components of the first vector on the top row and the components of the second vector on the bottom row for each of their I, j, and k components. So to find the I component of n, we're going to cross multiply what's in yellow. So it's going to be 1 times 2 minus -2 times -5, or 2 minus 10. To find j, we cross multiply what's in green. So it's going to be -5 by 8 minus 2 by -10. And this gives us -20. And to find the k, finally what's in blue, it's -10 by -2 minus 8 by 1, or just 12. So now we have the normal vector. And this is a vector that is perpendicular to the plane. So it's sticking out of the plane at a 90-degree angle. So we're going to use the equation that we saw earlier along with a point, OP, which is going to be 10, 2, 0, and we're going to plug everything into the equation. So A, B, and C are going to be the components of the normal vector, and on the right side, it's going to be the components of the normal vector times the components of our starting point. So it's going to give us a constant. And then from there, we simplify, and we end up with this equation for the plane. Alright, so the last step to the second approach is to plug in the points into your equation. So with this equation, we can actually plug in the points and verify to see if they're on the plane. So let's go ahead and do this for all three of these points. So for P, x is 10, y is 2, and z is 0. So it's going to give us -20 minus 10, or -30. For Q, x is 18, y is 0, and z is 2. So it's going to give us -36 plus 6, and that checks out. And finally, for R, we get x 0, we get y is 3, and z is -5. So we get -15 minus 15 equals -30. So that's true. So now we know that these 3 points lie on the plane. So just to recap, we covered 2 approaches to finding the equation of a plane that passes through 3 non-colinear points. The first approach used a parametric equation that relied on 2 variables, while the second approach used the dot product of the normal vector and a vector that was parallel to the plane. So if you thought this video was helpful, make sure to like and subscribe so you don't miss the next video.